Hi, everyone, and welcome to today's webinar, Analyzing and Specifying Interfaces with MBSE, presented by Fran McCafferty. My name is Donna Long, and I will be your host during today's webinar. Fran is a practicing principal systems engineer, leveraging experience gained over a 30-year career. Fran was one of the early pioneers in applying model-based systems engineering, serving as the GE-era Strategic Defense Initiative Requirements Manager. He has also led numerous project architecture development efforts for commercial, U.S., and foreign defense projects. Before Fran gets started, I have a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the Question tab on the webinar control panel. Fran will answer as many of these questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be made available within 1 business day. The recording will be published to Vitek's webinar archive, located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to Fran. Welcome.
Good morning, folks. As Donna said, I'm Fran McCafferty, and I'm glad you could attend today's webinar on analyzing and specifying with interfaces with MBSE. So one of the things that we always look at is the problems with overall modeling and understanding systems is there's often issues when it comes to how does my system under design interact with external systems, or potentially how are the subsystems in my design interacting with one another. So today's discussions will be focusing on how you might model some of these concepts inside of an MBSE environment, specifically core. So a lot of people have asked, well, I understand the concepts of interfaces, but what I don't understand is inside of the MBSE, what's the right technique and how should I move my information from one place to another and capture the design details and perform the overall analyses. So during today's discussions, we're going to look at predominantly 3 specific areas. There's a logical interconnection between things, there's a physical connection between things, and then there's always the intelligence passing between them. So what we're going to look at is constructs that are inside of GENESYS that help us model those concepts clearly and efficiently, providing us with the detailed analyses so that our designs don't get to integration and test and have the serious issues where things just don't communicate. What I'm showing you on the screen now is a representation of some of the constructs that are inside of the MBSE schema. Now, there's lots and lots of other things related to the schema, but for today's discussion, we're really going to focus in on 5 concepts. So for instance, we have our functional ideas where that represents things like hardware elements and its software elements. It could be your overall system, it could be external systems. We also want to understand how are the things interrelated. So we have an additional object that is the interface that represents that we have a logical connection between 2 things. All we're saying that there is connectivity. We'll talk about how in a second, and that's where we use the construct of a link. A link represents that there's some type of physical interconnectivity, and there may be multiple ways, and those are all fine things to capture inside of your design modeling. So on that side, we've sort of are looking at the overall physical constructs with the component, interface, and link, but we also want to be able to associate what our system is doing through the behavioral. And when we refer to behavioral, we're specifically focusing in on things like the functions. Functions are doing something in our system. And then we have items, which are the traditional inputs and outputs of a function. And we captured lots of detail with those, and there's characteristics that will follow as well. Now, we refer to the interconnecting, the flow of things as an item, and it's specifically termed that way because an item may be a message, which is pretty much the focus of our discussions today, but it can also be used to model electricity going from one place to another, or it could be hydro or fluid dynamics type of things going through a pipe. So anything that has transmutability, we can capture with this the item construct. So let's start off. You know, in any design, we're looking at concepts of components. And again, the component could be your system under design and its environment or external systems, or it could be something inside of your design, something like a subsystem, where you could break it down pretty far where it's a line replaceable unit as a hardware construct and the software going in between it. The primary emphasis that we're trying to make here is that we know that these things are going to talk to each other. We may not know all the details of the specific time in our design evolution, but we absolutely know that we have these two things that are going to exchange intelligence between them. And what we're just saying is that the construct that we're using is the construct we call the interface. And we'll go into that in more detail. And so, by the way, you're able, inside of the GENESYS design methodology, components can be decomposed and so can interfaces. So we can capture the information at the level that makes sense for the modeler. It's not that it only applies to the very high level abstract and it excludes the low level detail, because that's absolutely not the case. We can model throughout the entire evolution of a design system. Next, what we're going to talk about are the behavioral constructs. So traditional functional analysis, a function has inputs, it processes, it does something to that information and generates potentially one or multiple outputs. So we're doing the same kind of thing here. I'm just representing that I have a function on the left that's function 1 and one on the right that's function 2, and one function generates a trigger for the other, and then it processes and generates information or intelligence back to the secondary or receiving function. One of the subtle difference that I would like to highlight too is that information or the intelligence that's going across can be modeled in terms of triggering events, such that function 2 may have to wait until it actually gets a message before it can actually execute. Or the information may be something that's more persistent, where you're looking at an inventory that does change over time, but it's not the absolute controller of the execution or how the flow is going to take place. If something's there, we're good to go. We're just going to look at what information is in some type of data repository. So we capture that information as a data store. Now we're going back to our handy dandy components, component 1 and component 2 again. Through the interface, we talked that there was a logical interconnectivity between them, saying we know it's connected, but we don't know how. Well, this is the next peel of the onion. And what we do in this domain with the physical connections is we model how that component is talking to another component using a construct that we call a link. Now, with a link, we are in the physical domain. We can put on a lot of parameters that are associated with what's going to go across, like bandwidth and so on and so forth. We can put in directionality. It could be single direction, bidirectional, whatever makes sense for that specific modeling area. So to give you a concrete example, consider that you're in an industrial complex and there are two buildings, and these two buildings are going to interact with one another. So knowing that they're going to interact, we have the interface. Now the next step is there may be a reason that we have to exchange files per se. So beneath the ground, we might have an Ethernet cable that's copper. It's 10 base T or 100 base T, whatever is necessary. So that can be represented as a single link. Now we may have something that requires higher speed, and we might want to introduce a fiber optic connection between the two buildings. So another underground connection has that physical copper or fiber or sets of fiber beneath it, and that may carry the same kind of data. But maybe we have a backup plan or something we don't want to have any exposure to the public internet, and we want to put a microwave antenna on both of the buildings, so we have a connectivity there. So we're looking that the building has an interface logically, but inside of that we have three separate links that could transmute information across the path. We have the Ethernet fiber, we have the Ethernet copper, and we also have a microwave. So all three of those could represent the links that are inside of it. And then we may determine that based on some type of rule, whether it's a priority and availability, a size, something that are business rules that your organization determines, says how that information is going to go through, and we may use one as primary and the others as backups, or some other rule-based concept that you're going to look at. So in other domains, we're all familiar with with requirements decomposition. We have high-level ambiguous requirements, and we're going to decompose those down to the point where they're standalone, unique, and testable. That's fine. We all understand we do things inside the functional domain where we decompose abstract functions down to the point where we have very clear allocatable functions. Same thing in component-wise. The hardware breaks down into a bill of materials with levels of abstraction. What I'm going to show you on this slide is you do something very similar with intelligence transfer. The connectivity model is also going to have levels of hierarchy. And what I'm trying to show you here is, unlike the function or the component that has decompositions inside of the same kind of object, connectivity takes into account three different aspects: the logical interface, the physical link, and then the item as being the behavioral element. And those things are all interrelated because the item is transferred by the link. So we can put in characteristics regarding how that's going to execute. So now let's bring it all together. Well, it's great that we can do a functional analysis or a physical architecture. We may have some ideas of what information is going to flow, but now, when we're in our system analysis mode, we want to bring these things all together because they're not unrelated. An effect on one of the parameters affects something else in the design. So what we look at is to tie the functional to the physical. Functions are allocated to component, and we've talked about how a function will generate or receive an item, and that the item is now carried over a physical medium, a link, and that the physical links are associated with an interface. So we're tying those different domains together, and we can perform analysis. GENESYS has a discrete event simulator that we're able to execute the behavior of a system and take into account some physical restrictions that might be associated with it. If we have a great big file, and we've seen this where we try to send enormous emails and it takes a while for them to get across over a link, that there's a throttling. It's not instantaneously, there is a delay, and we can model those concepts inside of our MBSE world. What I'm going to do next is I'm going to show you some of the views in a static format, and then in a little bit I'm going to take you over into GENESYS and show you how you would maneuver through the environment to see the different concepts that are going on inside of here. So what I'm showing you on the left-hand side is an interface flow block diagram. And what I'd like you to focus in on is the system under design is the geospatial library. But the geospatial library doesn't live in a vacuum. It has interactions with other things. So for the model, we've identified that we have three separate interfaces from the geospatial library to those external environments. So we have a certification authority, we've got customer, we've got collectors. So we've identified that we have three independent interfaces from that system to all the other external systems that are affecting our model. Just an adjunct for a moment. For folks who are current or in past have access to GENESYS and Core, we always deliver the geospatial model. So things that I'm showing you here on the diagrams, you'll be able to go back and look at the concepts in your own time frames and understand how the interconnectivities are there, and that you can use those as templates for when you're going to do your own modeling. So one of the things I'd like to point out is we give you the options that you can look at the components on this screen, the geospatial library or the customer, as an icon, but you can also look at these things in a block construct. So that's really up to you and how you want to look at the information. So what I'm going to do additionally here is that we have the collectors interface open, and that is the, let me see if I can turn on my pointer for you so you can see what I'm highlighting. So we're looking at the collectors interface. We notice that it's associated with a geospatial library, and it's also associated with the connectors. So for an interface, it has to have exactly two connections. We'll allow you to have one at a time, but it won't allow you to have more than two because that's a violation of the rules of connectivity that we've established. So I'm showing you the graphical representation. And by the way, folks, you're able to do your modeling in multiple ways. So for instance, folks who are more graphically oriented, they can create their boxes and then point and click to make the connections. Other folks want to go through and model their information textually and establish relationships through the through a text-based environment. And for our perspective, all are equally useful. Use what is available to you in the context that makes you happy. So what I'm going to do is on the property sheet to the right here, we notice that there's a series of relationships that are possible. What I want to emphasize is that for this example, the logical connection for the collectors interface, we can see that it joins two separate components, the collectors and also the geospatial library. So we're establishing the first level interconnectivity. This is the logical connection. What we'll show you in a moment is that it also has the physical connection that an interface has a decomposition, or an association is probably more accurate, with the link construct, and you'll see that the link is associated with that particular interface. Now, when we transition once again over into the physical connectivity connections, you can see that you have more than one link that's going between two constructs, or components in this case. So we see, for instance, the workstation has two links that are traversing it over into the certification authority. So we can model what happens associated with those links. And what I'd like to point out on the property sheet that you can see very clearly is that we can establish that there's a capacity for the link. The link isn't limitless in what it can do. We can model those things and capture requirements associated with it and see if there's an effect. Very often when you're doing a discrete event simulation, do you start to lose the resolution because timing is off base? So we can capture what the capacity of a link is, and then also the capacities units. We leave it dimensionless so that you can model it the way you see fit. And then also in the bottom, you see that we have the link is comprised, it's part of an interface. It connects two components. It may have other additional link information associated with it, and you see that it's transferring a specific item, the certification request, across it. And that brings us over into the behavioral world, or information or item exchange. So this is where the intelligence actually is being manipulated. What I have on the left-hand side is an activity diagram. Folks should very often are familiar with. The larger boxes represent the functionality that's being executed inside of the specific modeling capability, and the smaller boxes represent the items, the inputs and the outputs of the functions. So it's not enough just to know that a function has inputs and outputs. We also may want to know additional resolutions of information. So for instance, when I'm going to transfer the certification request message, I'm saying that it has a specific size, and I'm declaring that it's in megabytes. So this is a really big message that I'm going to move across the link. And I have reasons for wanting to understand that level of detail, because it may have impact on how much resources that I need to have, redundancy as an example, how much redundancy a system has to have in order to move this kind of data, and what happens as we ramp up the contents and also the quantities of the messages. I wanted to take a moment also to show you that inside of an item, we can have additional level of resolution. So for my example, and I just did this haphazardly, is I added in 4 separate fields that are contained inside of the item. So I put in that there's a header, and then there's a body, there's a checksum to make sure it came across, and then I have an I'm done goodbye world message that's associated with it too. So that's one technique that you can associate additional levels of resolution. And it's by the way, you can also decompose your items further using child relationships. An item decomposes into further levels of items. So it just depends on what level you're trying to model, what you're going to include in your item strings. So let's go back to the elements, relationships, and attributes. We focused in on the 5, and we saw that we model in the functional domain, the physical domain, and also the logical domain. And at this point, just showing you that we can show you that things are interconnected because functions are allocated to components. The component is joined by interfaces, and interface is comprised of links. So we're tying all the different domains together. And just to reinforce, You don't have to know everything at the beginning. As one of my colleagues says, start with what you know and then move into what you don't know. So as you understand more about your system, you add additional layers of resolution and detail into your model, and you're capturing it through these structures so that you can determine whether you're complete and that your consistency is where you need it to be. And we're doing all of this inside of one design environment. In this case, it's GENESYS. Before we go into the actual tool base, I also want to show you that you're able to look at what happens with the interconnectivity. So on the top left, what I'm showing you is that I have an enhanced functional flow block diagram. It has two functions that are executing in parallel, and the green item -001 represents a triggering message that's going from the top, the transmit function, over to the receive function. That's the behavioral domain. When I go into the bottom block, I have a physical block. I have two physical components, one's a receiver and one's a transmitter. Then they are associated with link 1. So that item is going over link 1, and we'll look at the characteristics. So on the right-hand side, we can see what dependencies exist that a function may have to wait for its triggering message. We can see how long that specific thing is taking to cross the linkage because of the size of it. You know, if we have a gigabit message and we have a 10 megabyte pipe, it's not getting there instantaneously. We have to do the simple division, which takes up time, and it also consumes some of your bandwidth. So we can model those characteristics inside of GENESYS and see the timeline effects, performing analysis, and we can also generate a transcript so you can evaluate if there's somewhere that you think you would be better served adding additional functionality and hardware, or so on and so forth. So what we're going to do now is we're going to take a jaunt over into GENESYS, and I'm going to show you how the information can be captured inside of the tool. For folks who have been using Core and GENESYS, what I'm starting out with here is the Project Explorer, and this is our navigation window where we can get to any parts of the information that we see as relevant. So throughout the discussions, we've been saying we work with things inside of an overall hierarchies. We're looking at physical architectures, behavioral architectures, requirements which are outside of the scope of this specific example. So what I'm showing you here is I'm starting off with an external context function. And everything is in generic terms just so that I don't confuse folks who are working one layer or another. But what I can see inside of here is that I have an outer container that is composed of potentially my system under design and some external world. So I'm capturing that I have a physical hierarchy tied into here. Now what I'm going to do is I'm going to go over and bring you to a logical domain. So if I expand here, now what I see is that this component 1 has an interface to something else, and it also performs some functionality. So I'm tying the different domains together, the behavioral to the physical. Logically, I have the interface. Now, if I expand what's going on inside of my interface, now I can see that it is comprised of specific links. So I have link 1 and link 2, bidirectional, single direction, whatever's necessary for your design. And then I can bring it to the next layer, and I can show you that I have the item traversing the link. So I have my behavioral objects, my physical objects, and logical objects all interrelated inside of one design. So I wanted to show you how that construct looks inside. So now, one of the things we point out inside of GENESYS is that it's a single repository. All the information resides in here, but there's lots of ways of looking at your data. And I always refer to myself in system engineering is my job is a communicator. I have to communicate ideas that I understand to people who may or may not understand. So it's not enough for me to say, I'm going to tell you the way I want to, what I want you to do. I've got to be able to give you information in a form and format that you understand what I'm trying to understand. So I have to translate into the terms that you need, not the way I want to transmit. So if folks want to see information in a hierarchy, we can give you that capability. Then you can also look at things very specifically. So if someone were really focused on the logical domain, I can bring an interface block diagram and I can specifically see, okay, I understand component 1, component 2, yeah, there's a logical interface between them. So that's just one. Now what I may want to do is say, well, the next evolution is I want to show people that there's a physical interconnectivity. So there's my component 1 and 2 again, but this time what I'm showing is that I have links going between them. And those are the physical things. They're pipes, they're whatever is necessary, the cables to get the information across from one point to another. There's also the concept of ports. So let me take an adjunct again and think about things like your laptop computer. We have multiple USBs on a computer these days. So if we're going to model something like that, it's important to know that we've got component 2, but we also need to understand that it has ports that are going to exchange information. So you're able to designate what's the difference between USB port 1, USB port 2, and how that's going to be interconnected to something downstream or upstream for that matter. So we capture that information in a flow internal block diagram. So now that shows you that we've had the connectivity from logical perspective, from a physical perspective, but also we may have a need that we understand things in a behavioral mode. So showing you the activity diagram, we saw this kind of thing before. So in the activity diagram, I've got 2 process lines and functions on them, but what I'm showing is that I can bring the items going out of one and going over to another, and show you how that message flow is a critical concept that's being exchanged inside of these things. For folks who model specifically in the data domain, they very often want to see the information in a sequence diagram. So this shows you that the function 2 is sending over 2 informational items to function 1, and function 1 is going to send it as the third in the string. So you're able to capture the information the way people need to understand it again, not so much that you're trying to show them one and only one way to represent the data. Give it to them the way they want. So now what I'm going to do is, sometimes there's an instance where I have to go over and I'm going to look at information in a separate way. So we've talked about looking at data at hierarchies, levels, and levels of abstraction, but there are times when we've got where the interface starts to become the real critical design. Maybe it's the focus of your design. So for this one, I'm giving you a really simple example of an Ethernet connections. So for instance, I have a router. It has a cable that's going to be Ethernet, and then that's going to connect over to a computer. Now, this is a really low level of resolution, but in some situations, people need to have that level of detail in order to avoid building cables incorrectly. My past history, I've experienced where the cables were one of the largest areas of redo because people interpreted the information not the way we actually intended for them to see it. So now what I'm going to do is I'm going to take you over to breaking this information down into a higher level of detail. So for instance, if I have my Ethernet connection, we're always going to have our A port and our B port plug. So then the next step is, what are the things going through this? And what I tried to do here is, using the TIA standard, go through and identify what are the actual conductors that are going through from the left-hand side connector A to the right-hand side connector B. How's it going to be wired? We could go in and put levels of resolution of which ports it's going to be. Are they going to be the same order on the left as they are on the right, so on and so forth, so that you have a level of detail and resolution that makes sense for your level of design. So that was what I wanted to try to go through and explain to folks on that design. The next step is, I guess, is going back and looking at some of the as a little bit of a recap. So again, we always understand that you're able to decompose things at the requirements, functional, and physical domains. Those things are really obvious to a lot of folks. And where we get caught up is in the interfacing between them. What's going across boundaries? Who's got the management responsibility? What have we agreed to? So we're capturing those things at multiple levels so that people can understand it as the design evolves from abstract to rather concrete. So we're looking at things like the logical construct, the interface, the physical construct, the link, and then, for instance, in this one, a message is captured as an item. So again, we can model these things as they interrelate to an external system that's outside of our control, or it could be within subsystems that are inside of our control, where we're at the higher level system engineering activity, we're defining what the boundaries of the subsystems are, and we would control what is going between the two subsystems so that that overall pedigree at the system level is maintained at the detailed design levels. Within GENESYS, what you get is the representation. You can generate a whole series of views that look and behave the way you want them to look and behave, and communicate the ideas that are most useful to the people who are receiving that data, and avoid some of the really common errors that we have in the interfaces. Just as an example, in my background, at one point we were designing a system and we had settled on a parallel connection. Over time, there was a need to change it over to a serial, and what happened is one side made the transition to the serial connector. When we start to go to next levels of detail at a CDR, we identified, oops, we have a problem because the transmitter is serial and the receiver is parallel. It's just not going to work, and we had to reevaluate the methodology. So inside of a tool like GENESYS, you're able to see that level of detail and prevent those downstream errors from being something you don't see until you physically try to cable things together and have that all too familiar, oops, didn't realize that was going to happen situation. So again, we're also able to look at things from the very, very high level abstraction of systems talking to each other, or modeling it down to the very high resolution where you have a physical interconnectivity between two boxes, or maybe it's the actual interface is the object of interest and you need to really focus in on what the details of that thing are. So one more here. Again, I'm Fran McCafferty, and you can see my contact information here. We'd love to hear from our customers on their thoughts that they have about what they've seen, and even with some of the scenarios, maybe there's things that you've done that have been beneficial or that you may want to recommend over to us. So we have some time left, Donna. Is this a good opportunity that we would go into questions and answers?
Thank you, Fran. We do have a few questions thanks to our participants. I encourage you to join the discussion now and submit your questions using the webinar control panel. If you do need to leave the webinar, please take a moment before you go to respond to the quick survey that will pop up on your screen. Our first question comes from Mike. Can interfaces and/or links be decomposed, and why would you do that?
You absolutely can decompose both of those object structures. And the reason you would do that is because you have levels of details. For folks who are familiar with Vitek's leveling approach, you have high level abstraction. So we would have from the external system to the internal system, we have an interface that's comprised of links. When we go down to the next layer of detail, we can also show connectivity from those secondary decompositions. The external system may have some major concepts inside of it that we want to associate and really understand how those traverse over into our system under design. So we can have hierarchies of interfaces and we can have hierarchies of links, just like other objects inside of the MBSE environment. Why would you want to do it? And it has everything to do with levels of abstraction. Early on, you have limited knowledge of what your system's supposed to do and how it's supposed to do it. Over time, you're going to add additional resolution so the model will track it and the decompositions of those objects support it.
Okay, and we do have a follow-up from Denny. Are there limits on how many levels you can decompose an interface, a link, or a data item?
Vitek's not going to impose any of those restrictions. Generally, it really depends on the level of modeling that you're trying to get to. Some folks won't build up the interfaces and links until if they already know lots about the lower levels of the design, but that's purely up to the designer how many layers they want to decompose and at what level they want to start and what level they want to finish.
Okay, the next question we have from Denny is, are interfaces usually assigned to components only, or can they be allocated between functions?
Interfaces are specifically between up to exactly two components. The interconnectivity between functions is the item. So when we actually have separations of concerns. When we look at the component, it actually lives in two separate domains, the physical and the logical. functions and items live at the behavioral domain, and there are associations which we've gone through during the examples, but an interface does not exist between functions. Items exist between functions. Interfaces exist between components as well as items do.
Okay. Our next question is from E. Walker, and it is for items such as message transfer in today's information systems heavy environments. Is it now typical to decompose messages into specific protocol elements, for example, TCP/IP packets and or signals?
Unfortunately, the answer on that is it depends on where you're modeling. We have had customers decompose where they're actually developing the protocols and showing how the transmutation of the information exists with the item. So for instance, on the one example I showed you where you could have different fields inside of an item that breaks it down. For my example, I used that I had a header, a body, a checksum, and a termination portion of the message. So it depends on what's important to you. If you already know that TCP/IP is fine, there may not be a real reason to model to that level. You need to model to the level of detail to prove that your system's doing the things that it needs to do. So again, the answer is it depends on what you're trying to prove. If I didn't have a real driving need to understand the details of TCP/IP, I would not model it. If that is a critical aspect of my design, then I would model it.
Okay. That was a good example. He responded. Okay, so a message from Mike. Are ports associated with links, interfaces, items, or only the components that provide them?
It's associated with the link. I'm going to reach out to my colleague. Donna is actually one of the experts when it comes to what I'm looking at is when I have, say I have a breakout box for an Ethernet hub, or let's use a hub as an example. So if I have the hub, I want to identify that I have 8 ports per se. And then when I go through my detailed design, I want to identify that I'm using port 1 for a specific purpose, so on and so forth throughout the others. So looking at the modeling of it, you're going to have a connectivity between the component and the link that you're building up the levels of ports. Did I explain that correctly, Donna, or do you want to add a little insight?
All I'll say for clarification is that it's really a triad because your link is using a specific port to get to your component. So we see that as a triad relationship where you identify the links, the components, and then the port that's in use between them. So I don't know if that made it better or worse.
Thanks, Donna.
No worries. We did have somebody else chime in. Ports are owned by the component, and the port connects to a link.
There you go. It's great to have peer inputs.
Yep. Anyway, okay, so I'm looking through the questions we have. Please, if you've got more questions, do send them in. We'll start at the top with E. Walker again. How easy is it to transfer the wire physical block diagram to a specification and then to a wiring diagram? Is this process streamlined for cycling through a design change management process?
The easy answer is to say yes. When you're looking at the wiring, if you're trying to generate, you asked actually there's like 3 different pieces. Donna, can we start? Let's start with the first
is it
part of the
transfer
question.
The wire physical block diagram to a specification?
Yes, because what we often want to do inside of the MBSE is we have the requirements hierarchy that says, hey, these are all the things that the system has to do, and we try to keep it clear that it's not saying how. So in my modeling experience, I would have a requirement call out that I have either the items or the links, that I have the association. So when I'm going through my proof points during testing, I can say I've met these requirements. Here's the manifestation physically that proves to you that I've built wires that correspond to the requirements that have been specified. What was the second part, Donna?
And then can you transfer that to a wiring diagram?
I think what you're going to look at is as you could see from the Ethernet, you can build some of those things inside of GENESYS. As you're going through, at a certain point, you're going to transition over into your CAD type of environments. But what we're offering is, before you transition over into a CAD environment, you're giving the detailed designer all the parameters that they need to understand so that you can push over into something. I think in the past I've used a Pro E with my teams, where we'd give them all the characteristics of what has to be built inside of a cable and then push it over to a Pro E so that they could actually do more detailed designs, like for how the solders are going to be placed, how the twists have to be performed. So you would go from GENESYS over into those detailed design packages is what I think you're asking.
Okay, we can get some more information from him, and we'll reach out to you after. Let's move on to the next question. When modeling interfaces, what tips and tricks would you recommend in naming items, connecting to requirements, starting from scratch for a new system, or starting with a legacy system?
That's a great question. And a lot of this, these are some of the things that we recommend that you capture in your system engineering management document, or SEP these days. So for instance, when we're looking at different object classes, you want to come up with a glossary. So for instance, in our geospatial library, we use FN to represent a function. We use an I for an interface, an L for a link. So at a certain point, we start to reuse the alphabet. Whatever makes sense for you to organize it, so that when you see things in a hierarchy, as an example I showed you earlier, you clearly understand that the object on the screen is a link, or it's an interface, or a component. So the numbering sequence is where I recommend you capture some of the concepts. Also, because we generally don't have millions and millions of interfaces and links, it may be worthwhile for the name to actually say interface colon and what are the two connection points, so that it becomes very obvious just looking at the short name description what this thing is and what it's intended to do. If you use cryptic descriptions and names, then there's additional opening and closing of windows to understand what that specific object's supposed to do for you.
Okay. The next question is from Koibus. It's interfaces and links should have requirements specifying them as you start fleshing out your design. How do you handle the traceability of these interface requirements through the layers of your MBSE model? Should interface requirements on layer 2 have interface requirements on layer 1 as parents, or are they design decisions on level 2 and may not necessarily have layer 1 interface requirements as parents?
I hate to do it again, but there's always it depends on what you're trying to prove your system is capable of doing. So if you have high level concepts that say thou shalt speak from external system 1 to your system under design, I would recommend you would have a requirement that specifies that interface. In other situations, if it's inside of the black box, where I don't have to prove that a specific interface exists or a specific link exists, and it's a design decision that's left up to me as the designer, I don't have a requirement that is pushing me from the external world. But I would recommend that you would create requirements that say why this thing exists, and mainly because it's not so much the first time through. The first fielded system has all the engineers who were making decisions along the way, but as you go through and are maintaining systems over time, that the next team that replaces you, you're able to go back and understand why did the organization do what it did, so that I know the boundary conditions for form fit functions. Why does this thing exist? If I replace it, what characteristics have to be maintained in the new design construct? The ECP will tell me what I have to maintain and actually what I have to test and prove. So again, it depends. If the customer tells you you have to have an interface to something, then you're able to show, okay, I've manifested the interface I'm associating with the requirement. At the next level, if there are higher levels of resolution, you can trace that way. Or if it's something you do at design decision time, then you're able to push it back and say, I did these things and this is how well I've done them.
Okay. Our next question is from Denny. DODAF models need lines between operational nodes in the OVO2 diagram. Can you model the interface as being equivalent to a need line?
No. And I'm glad you asked that, because what I didn't show today was that there are two different portions of the model. One is we have the operational architecture elements that are a higher level of abstraction versus the system design implementation. So on the operational architecture side, there is actually a folding over. There's a duality between the two sides. So a need line that you refer to needing in your OV is absolutely correct. A need line will define that there's a need for some type of link to exist between the system under design and another system or some other part of the model. So to generate your OV, you're going to have a different set of objects that are not unrelated to the system design. So a need line and a link are directly associated, and there would be two different parts of the model, because the operational architecture is generally saying what a system has to do. It's trying very hard to not say how. When we get into the system design, that's exactly what we want to do. We want to say how something is done. So we're establishing the connectivity from the abstract, what we want to do, through the how of the system design. If you have a question on that, we can actually show you in the operational architecture structures that we have what you would need to do in order to generate an OV.
Yeah, we just, the need line is implemented by a link. So that's how the connection is, as most of the system is to the architecture model. Let's see. Do you consider that Core or GENESYS have the same capability as the UML-based tools in terms of modeling the software interfaces? And this is from Well.
I would need to get back to him on that. I don't want to give an off-the-cuff answer. Software has not been the area of emphasis that I've looked at as much. So I have exposure to UML, but to do a one-to-one would take me more than just an off-the-cuff answer.
Okay. Ewalker had a follow-up. For your CAD answer, how easy would it be to transfer specs to a design build drawing software?
I think there's a reasonable, straightforward approach. I'm making an assumption that the CAD environment that you're working with has an API set. GENESYS and Core both have API sets. There'd be some level of mapping to make sure that it's giving you all the design details from GENESYS over into that design environment. Because the IDs are there. Good, Donna.
No, that's okay. Yeah, the API would be the way to do it, and the GENESYS API is a little more open architecture. So, let's see. We had the last question I have right now is from Sarah. Do I have to start at the logical level like you've shown in the example?
The answer to that is no. And going back to what my colleague often says, start with what you know and work to what you don't know. So if you know that there are physical connections that have to take place, then I would start there and model. The reason we go to the logical is to develop abstractions so that we can group things together so that the human mind can comprehend the scope and breadth of what you're trying to do. If, for instance, I only was working in the behavioral domain and that was giving me a lot of the insight that I needed to, I might do the functions and items analysis first, then go back and say, now that I've done this functional work, I start to see patterns, and I may want to organize the functionality in a specific way. Well, when I start to do that, I may be working in an area where I say, Based on what I see here, I'm now going to establish components. I'm going to say I've got an abstract component that does functions that are like X, and I have another component that does functions that are like Y, and another for Z. So whenever I start to organize my thoughts that way, that's now when I'm starting to say, well, does X talk to Y? Yes, so I have to have an interface. Does X talk to Z? No, well, there's no interface there, but Y talks to Z, so I have an interface. And then I'll have, what kind of transport mechanisms do I need to use? Do I want to use Ethernet or some other mechanism? So now I'm going to call out the links that the items are going to walk across to go from one part of my design to another. So it really is what do you know about your system? Start there and then move to the things that you don't know and build up your levels of detail from that point.
Okay, we did get a question in. You mentioned engagement with customers for use cases. How is the best way to start that interaction?
I think as a system engineer, your biggest asset is your ability to communicate with them. If they have specifications, we can often start with a specification. If they have an idea, sometimes it's a one-page summary document. We can start to go through and then ask them, is this what you mean? When I look at what I understand is I start with this function, I input process, the output is then used somewhere else. That's an input process output, so on and so forth. And I can show very often that the very abstract conversations are things we do on whiteboards. Well, that's great, but we always know what happens to whiteboards. We leave the room, somebody else comes in and erases them. What we're recommending is you start to institutionalize those whiteboard conversations inside of GENESYS. So when you're talking to your customer, you're putting the boxes on the diagrams and say, this is the functionality that we're going to perform. And if we need to give it descriptive text, we have the ability to do that. And if we're saying, well, when I'm done with this function, I generate some kind of intelligence, we can capture that into an item and then say, okay, well, where does that intelligence have to go for the next processing? So does it go to one function? Does it go to multiple functions? We can capture that level of detail dynamically, putting the core GENESYS up on a screen and short-circuiting the whiteboard or using it as an adjunct to the whiteboard as people are discussing. So I think you're showing them graphically how information is exchanged through things like the function or the component or the interface, and to get that level of understanding exchange between your customer and you.
Okay. We do have a couple questions about design structure matrices. I'm not familiar with that, Fran, are you?
I am not.
DSM. Okay, so we'll talk to you about that offline just to get an understanding of what that is. Thanks, Fran. That wraps up the final Q&A for today's presentation. If you have other questions or comments, please don't hesitate to send them an email. You can post your questions and comments on our LinkedIn group page. Just visit linkedin.com and then search for Vitec Corporation. Thank you so much for attending today's webinar. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you for joining us and have a wonderful day.
Cheers all.